Think about this for a second. How on earth do you measure an entire universe without checking every single star? Or, to bring it back down to Earth for our purposes today, how can we possibly measure a whole population without actually testing every single person or item in it? It sounds like an impossible riddle, right? But, well, that is exactly the problem that sampling solves.
Welcome to this explainer. Today, we're zooming in on the actual mechanics of research methodology. We're going to uncover exactly how studies actually go out and gather their data. We'll be moving from the absolute simplest methods of convenience all the way up to the rigorous, rock-solid mathematics of probability. Okay, let's dive into this. Here is our methodical breakdown for today. First, the impossible census. Then, the Great Divide, followed by the non-probability toolkit. Basic probability, advanced probability, and finally, choosing your design.
All right, let's kick things off with Section 1, the impossible census, and look at why we actually need sampling in the first place. The foundational difference here is pretty straightforward. A census enumerates, or counts, literally every single item in a universe, or a population, as researchers usually call it. A sample, on the other hand, selects only a fraction of that population to estimate the whole. Now, at first glance, you might be wondering, wouldn't a full census always be the better, more accurate option? Well, as the researcher C.R. Kothari points out, considerations of time and cost almost invariably lead to a selection of respondents. While a census might seem like the ultimate gold standard, it's honestly rarely practical. I mean, surveying an entire country, that takes massive amounts of time and budget. Plus, think about this. What if your test involves destroying the item? You obviously can't test the lifespan of an entire batch of light bulbs by burning every single one of them out. And a doctor sure can't drain all your blood just to run a test. So in real-world research, sampling isn't just some lazy shortcut. It's literally the only practical choice. Moving right along to Section 2, the Great Divide. This is where we look at probability versus non-probability. Now, what's really interesting about this slide is how it maps out the entire territory for us. Basically, all sample designs fall into two main categories based on their representation basis and the technique used to actually select the elements. Let's really contrast the core of this divide, because it's absolutely crucial. Over on one side, we have probability sampling. This relies heavily on the mathematical rigor of random selection, which means we can actually calculate our margin of error. On the flip side, we have non-probability sampling. This relies on deliberate, purposeful selection by the researcher. Sure, it's way faster, but it carries this inherent, honestly dangerous risk of bias creeping into the data. So let's open up Section 3, the non-probability toolkit. These are the fast, but potentially biased methods. First up in the toolkit is convenience sampling, and it is exactly what it sounds like, selecting population elements purely based on ease of access. Our source gives a fantastic real-world example here. Let's say a researcher wants to survey gasoline buyers. They might just pick a couple of fixed petrol stations nearby and interview whoever happens to pull up. It's super convenient to ground a study this way. But remember, if those gas stations are only located in high-income neighborhoods, your results are going to be heavily skewed. Moving on, we've got judgment sampling. Here, the researcher's choice basically reigns supreme. They use their own personal judgment to deliberately pick items they believe are representative of the whole population. For instance, a researcher might handpick one specific classroom of college students to test out a new teaching method. Now, this is great for early qualitative research, but the accuracy? It relies completely on the researcher having totally impartial judgment. Finally, for this toolkit, we have quota sampling. This is where interviewers are given very specific quotas to fill from different demographics or strata. They might be told, hey, go find 50 men and 50 women. But, and this is the kicker, the actual selection of which specific individuals to interview is left entirely up to the interviewer's discretion on the ground. Because it relies so heavily on that personal choice, it's essentially just a judgment sample wearing a disguise, which makes it incredibly prone to interviewer bias. All right, let's shift gears to Section 4, basic probability. This is really the gold standard of sampling. The absolute bedrock foundation here is simple random sampling. And this brilliantly illustrates how simple the concept really is. Think of it like a mechanical lottery. Step 1, you write every item's name on a slip of paper. Step 2, you mix them all up thoroughly in a big container. And Step 3, you draw blindly without replacement.
every single element in that population has an exactly equal chance of being picked. Now, sure, today we mostly use computer-generated random numbers instead of actual hats and paper, but that fundamental mechanical principle is exactly the same.
But what if you have a massive list and drawing names out of hat is just wildly impractical? Well, that is where systematic sampling comes to the rescue. It acts as a highly practical approximation of a true random sample. If you've got a list, you simply pick a random starting point and then select every ith item, like say selecting every 15th name on the list. You're actually only introducing pure randomness at that very first starting point.
Let's move to Section 5, Advanced Probability, and see how this builds beyond simple random methods.
This brings us to stratified sampling. Look, if your population is highly heterogeneous, which just means it's full of very different types of units, a simple random sample might actually accidentally miss a crucial minority group entirely. So what you do is divide the population into homogeneous subgroups, which we call strata first. Then you draw a random sample from inside each of those subgroups. This virtually guarantees that you obtain a perfectly representative slice of a really complex population.
So the crucial point here is understanding the difference between stratified and cluster sampling because they sound similar. In stratified sampling, we are pulling individual items from within carefully sorted strata. But in cluster sampling, we are selecting entire groups randomly. To use a great example from the source material, imagine an inventory of 20,000 machine parts stored in 400 shipping cases. Instead of randomly running around picking individual parts from all over the giant warehouse, you treat the 400 cases as your clusters. You randomly select a few whole cases, and then you just examine every single part inside those chosen cases. Much easier.
Now, a very close geographical cousin to this is area sampling. Let's say your area of interest is massive, like an entire state, and you obviously don't have a master list of the population. What you do is divide the map into smaller, non-overlapping geographical clusters. You randomly select a few of these local areas and then survey all the units within them. It makes field interviewing so incredibly efficient because your researchers aren't driving back and forth across the entire state all day. And actually, if researchers then randomly select individual houses from within those chosen geographical clusters, it becomes what's known as multi-stage sampling, which just adds a whole other layer of efficiency. Wrapping things up with Section 6, choosing your sample design and balancing the trade-offs. At the end of the day, picking a method ultimately comes down to a stark set of trade-offs. You're balancing time, budget, and accuracy. Probability methods yield estimable error and high accuracy. You can mathematically trust those results, but they cost significantly more money and take way longer to set up. Non-probability methods, they are faster, cheaper, and way easier to execute in a pinch, but they carry that very real risk of high bias, which honestly could render your entire study completely unreliable. Which leaves me with this final thought for you. The next time you see a news headline screaming about some brand new poll or study, I want you to look past the big, bold numbers. Ask yourself, how exactly did they sample the universe? Was it a rigorous probability design, or did they just grab a convenient quota of people walking past a gas station? Knowing this kind of academic taxonomy connects directly to your everyday consumption of statistics. Thank you so much for joining me for this explainer. Keep questioning the methodology, and I will see you next time.